Hello, in this video, we are going to look at another example. This time, instead of 2-point charges, we're looking at 2 charged spheres. This is from Winter 16 or ON16 paper 41. So let's read the question together. Two small solid metal spheres, A and B, have equal radii, okay, and are in vacuum. Their centers are 15 centimeters apart, so it's clearly marked out inside your diagram. Sphere A has a charge of positive 3 picocoulomb, so it's probably worthwhile to remind ourselves that pico is negative 12, micro, nano, pico, negative 6, negative 9, negative 12. Okay, so 10 to the power of negative 12. And sphere B has a charge of 12 picocoulomb. Arrangement is illustrated. Point P lies on the line joining the centers of the sphere and is at a distance of 5 centimeters from the center of sphere A. Okay, suggest why the electric field strength in both spheres is 0. So this is a very common past year question. If you've watched our level 2 examples, you would notice that, hey, this one quite common, quite familiar. And then you'll be right. So this is a pretty standard answer. So think about the metal sphere. If let's say you have a charge inside the metal sphere, the charge is not going to move because it's being pulled equally in all directions. So the first point that you should write about is that the charge inside the metal sphere, any charges inside the metal sphere do not move. That would be the first point. Okay? And because the charges do not move, you can then infer from basic Newton's first law. If the charge is not moving, the motion is not changing. So you can then say, hence, there is no resultant force on the charge. And you can then say, hence, no electric field in the sphere, inside the metal sphere. All right. So this one is one mark. This 2 would be the second mark. So the idea that you have any charge that's inside a metal sphere, let's say you put a positive charge here, this charge is not going to go anywhere because it's being pulled equally in all directions. Let's say this sphere is negatively charged. So all the negative charge is on the surface. Go and watch our video on Gaussian principle. Okay, so the positive charge is being tugged by all the negative charges that are distributed along the sphere. So it's going to be pulled in all directions. So at the end of the day, it doesn't go anywhere, right? So because it does not move, there's no resultant force. Hence, there's no resultant electric field, no electric field strength, or the electric field is 0. Okay, so no electric field. So hence, E is 0. All right. Okay, we're going to move on. So we know that inside the sphere is 0. But what about outside the sphere? Obviously, it's not going to be 0. Okay, so show that the electric field strength is 0 at point P. Explain your working. Okay, so CAIE has this way of giving you this sentence, which I like because students oftentimes, when in your study of physics, you might detect certain patterns and then you go and memorize. Like, oh, I know, I see this, I put that. We will be able to suss out these kind of students because we're trying to make sure that you understand your physics, okay? So electric field strength is 0, meaning the net or the resultant electric field is 0. How do we find the resultant electric field again? So let's say we take point P. Now, sphere A is positively charged. So the electric field is pushing, okay, hang on, camera is flipped, pushing to the right. All right, so this electric field EA is to the right. Positive, push away to the right. This one is also positive. It will also push away to the right. So this would be EB. Okay. If your electric field, your resultant electric field is 0, so here your EP at this point is 0. It means that EA and EB, because they act in opposite direction, they cancel out. It's a bit like if you want to do a thought experiment. Let's say point P is a positive charge. Okay? And both sphere A and sphere B is pushing point P away. Sphere A is like, here, I don't want this positive charge. And sphere B is also, here, I also don't want this positive charge. And at point P, the repulsion force is equal in magnitude. So if you put a positive charge at point P, it's not going to go anywhere, it's going to stay there, right? Because the resultant field is 0. Very much like in the center of a charge sphere. So we're going to use this right now. We'll put the EP is 0. So hence, I can then say, so this E is EP lah, okay? E at point P. So electric field A plus the electric field B will be equal to 0, all right? So we're going to go back to the diagram, and this one I will put K, QA over the distance of from A to P square, okay? Recall that the equation for electric field strength is KQ over R squared, okay? So here is where I need to talk to you a bit first. Number one, these two are in opposite directions. So I think we'll just put a negative sign in front of EB, okay? So then I'm just going to go back here and assign the negative sign here, okay? So this negative sign has nothing to do with polarity, okay? It's about the vector, all right? Once again, if you have not watched the other videos, I would just like to remind you that positive and negative sign means different things in different contexts. Like in this case, this negative sign, it has nothing to do with the polarity of the charges. This one is the direction of the electric field strength due to point charge B. Alright, sometimes the negative has to do with polarity, sometimes the negative has to do with work done. We'll see that in the second part of other examples, I guess. So from here, this one I can then include a negative sign, negative KQB over the distance. Okay, you can use big R, capital R, you can use lowercase r, it doesn't matter, from B to P squared equal to 0. Alright, so when you say explain your working, right, the explanation is here. You show the working that you understand that is in opposite direction. Because then what will happen is I will move the equation a bit. Okay, the distance from here, this will be equal to K QB over the distance from B to P squared. So this and this can cancel out. Alright, so now we need to check the ratio. Okay, so what you can do is you can say hence the ratio, I guess a better or a more efficient way of taking ratios is to ratio the same physical quantity because they will have the same prefix or the same units. That way you can cancel out. So I'll take QA over QB. It will be the same, should be the same as the distance of R from point A to P and R from point B to P squared. Okay, hence, let's check. The ratio of QA over QB. What is this? So we'll go back to the question, and you will notice that QA is 3 picocoulomb, QB is 12 picocoulomb. Okay, so QA over QB is 3 over 12. So 3 picocoulomb divided by 12 picocoulomb, which is 1 over 4 or 0.25. Right? Okay, moving on. This 1 over 4? Is it 1 over 4? Just to be sure. Sometimes full of self-doubt. Alright, 0.25. Again, habits lah. Don't write in fractions. Alright, repeat again for this one. RAP over RBP square. Okay, so what is the distance from A to P? Let's go back to the picture and see. A to P is 5, okay, and B to P is 10 cm. So this is RBP and this is RAP. All right, so AP over BP is 5 cm over 10 cm. So AP over BP, 5 cm over 10 cm. So this is what I meant by if you divide by the same physical quantity, you kind of don't have to bother about the prefix or the units. You just divide them, and then this one square. Well, this one also happens to be 0.25. Okay, so you can say since the ratio of QA over QB is equal to R, the ratio of the radius or the distance squared, hence the electric field strength is equal to the magnitude of the electric field strength is equal to EA is equal to EB, and we need to talk about, because it's not just about the magnitude, it's also about the direction. See this part, we're talking about direction. So you just want to be safe and cover your bases, and you can also add on a point and say that N both fields EA and EB are in opposite direction. Okay, so both EA and EB are in opposite direction. So this is 3 marks, so I think it is safer to backtrack like this. So show all your working. Okay, so let me explain. There are many ways to do this question. Of course, you could substitute values in here because you have QA and R, or QB and R. You can find the values and say, see, the values are the same. So do what you need to do to prove this one is 1 mark. Okay, so when you prove this, for me, I use ratio method because I don't want to come up with weird big numbers and it's just a bit inefficient. Of course, you could always find the exact value of EA and EB and compare them. That is okay. You will get around 10.79 Newton. Okay, so plus suitable proof. Whatever that suitable proof you decide to do. So if you're like the Miss, I don't like ratio, I don't feel very safe. Since I have enough numbers, can I not plug it in and find EA and EB? Go ahead. Okay, make sure you don't make any calculation error. Can already. All right, so this one can. You show suitable proof. So my suitable proof is such that ratio of Q, I show here lah. Like for example, I say that since or if EP is 0, then EA will be equal, EA plus negative EB will be equal to 0. Okay, so then I come up with this ratio. And based on this ratio, I calculated for charges and RA, the ratio of the distances, and find that they are the same. Now, if they are the same, ding, ding. So this one and suitable proof is your 1 mark. Okay, actually, if you show two suitable proof, this is actually 2 marks. Okay, so any kind of suitable proof that shows the magnitude of EA and EB is the same. Of course, you could calculate them separately if you don't want to use ratio. The third mark, because this is 3 mark, is when you talk about the direction. Both fields are in opposite direction. This is the third mark. Okay. Of course, if I'm a lenient examiner, I would understand based on the fact that you included a negative sign here that they are already in opposite direction because electric field is a vector. Or if you want to, you can just put a footnote like what I did here. Direction of EB is opposite to EA. Okay, so there are many ways to show this. I would prefer if the workings are clearer because it's easier for the examiner to see. All right, so you find a way to show that E and EB is the same plus a suitable proof. You could find the magnitudes separately and make a comment about the direction. Okay, both fields are in opposite direction. Okay, why are they in opposite direction? You might be wondering. You could say due to both charge having similar polarity. So if you are feeling insecure, which I often do, and normally students will as well, especially if you don't know where the marks are, write everything. Okay? Alright, so but this part is not needed in the mark scheme. The mention of polarity. Okay, so as long as you mention that the fields are in opposite direction but equal magnitude, you can show that they cancel out. Alright, calculate the electric potential at point P. Aiyo. So if you want to find the electric potential, which is Vp, you will take the potential due to charge sphere A plus the potential due to charge sphere B. Means direction, my friend. This one is scalar. So scalar don't care about direction, but you have to substitute the polarity. Okay, but the good news is they are both positively charged. So here is KQA over RA square plus KQB over RB square. And it's at P so this is BP and AP lor. Okay, so I can factorize the K. The K is 8.99 times 10 to the power of 9. Okay, then I put a big bracket. QA is 3 picocoulomb. I don't need to scroll lah. You can show you. Refer to the question on your phone. Okay, 3 picocoulomb QA, 12 picocoulomb QB. Okay, let's write that down first. 3 times 10 to the power of negative 12 plus 12 times 10 to the power of negative 12 divided by, oops, potential don't have square, my bad. My brain worked too quickly. There we go. Okay, so if you're a type where you're easily confused, I would suggest always writing the equation at the side. So in case I don't know what happened to you, you substitute wrongly. Always put the equation here as a backup. Alright, so KQ over R, no square. Alright, let's continue. The distance from A to P is 5 cm. So 5 times 10 to the power of negative 12. And the distance from B to P is 10 cm. Okay, negative 12, negative 2. 10 times 10 to the power of negative 2. Set to adjust this. Okay, there we go. Alright, you could be tempted to press calculator, but I'm a boomer, so I like to simplify a bit more. Vp is equal to 8.99 times 10 to the power of 9. Okay, I look at this prefix, right? Negative 12 over negative 2 is negative 10. So I'm just going to divide, multiply the whole thing by negative 10. Okay, this is why scientists use prefix, because we can take out the prefix. Take it out. Alright, so anyway, negative 12 divided by negative 2 is negative 10. So I take out negative 10 So what is left inside there? 3 over 5. Easy to press calculator lor. You know why not? Because if not, right, then when you press your calculator, you might not bracket your numbers properly. And what happens? All the answer, lintang buka. Or you will get a wrong answer. Alright, so I'm going to press my calculator now and find that my answer on my calculator is 1.62 or 1.618. Write 3SF lah. 1.62 volt. Okay, try to keep your answer in 3SF because who knows, maybe you need to use it later. Alright, so this is a simple application of equations. Just make sure that for scalar, we substitute polarity, which is the plus minus. Whereas electric field strength is vector. So no polarity. Consider the directions. Okay. Alright, next. Okay. A silver nucleus. 10747 AG has a speed v when it is a long distance from point P. Means how long is long? Okay, when they say long, infinity. Far away from the influence of charges A and B. Just like wherever you are studying now, you are a long distance from your teacher. I am at infinity. I don't know whether you are doing work or not. Use your answer in C, okay, which is the value of 1.62 volt, to calculate the minimum value of speed V such that the nucleus can reach point B. Okay. Let's steal the diagram first. Okay, I have stolen the diagram or found the diagram. Okay, so we're going to move this silver nucleus from infinity, okay, I don't know where is infinity, but let's say infinity is here. Infinity. So the silver is here. Sorry, a bit small. We're going to move this silver to point P. Ding 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 ding. Bloop. Okay. What is how okay, what's the minimum value of V? Alright. So I guess the first question is you might be thinking, Miss, wait a second. This silver nucleus, they never give the charge leh. They no give charge. Okay, you come down first. If it's a nucleus, think about your AS. It means that it has no electrons, okay? Ladies and gentlemen, boys and girls, meaning the charge here is positive 47. Alright, nuclear number positive 47 multiplied by the electronic charge, which is E. Boleh? Okay, so we're going to move positive 47 from infinity, and we need to park it here. Positive 47. Yeah. Okay. So next part. Long distance, infinity. Do you know the potential at infinity? 0. I mean, come on guys, look at the equation. KQ over R. When R is very big, V becomes 0. Okay? So when this one tend to infinity, this whole thing becomes 0. Alright, so let's go back to the picture. Picture time. Alright. So I'm going to move positive because this is a nucleus. 47 electronic charge, positive 47E. We'll multiply later and change it to Coulomb. Don't worry about it. Alright. So we're going to bring it from this side where V equal to 0 to this side where V is equal to 1.62. Did you increase the potential? Okay. Yes, we did increase the potential. We are bringing something from infinity and put it here. So who needs to do what? It has to be done by an external force on the electric field. Meaning, whatever that is happening, it has to be work done on the electric field by the external force. Okay? How do you know there's work done on the electric field? Well, because we went from 0 to a higher potential. It's like you climb up a hill ma. You go from the bottom, which is 0, and you want to climb up to 1.62. You need to do work, right? So work done on the electric field by an external force, but external force, so by the silver nucleus. Meaning this silver nucleus will suffer a decrease in kinetic energy. Because whenever there's work done on the electric field, when I do work on you, your energy should increase. So work done on the electric field means there is an increase in electric potential energy, meaning there will be a decrease in kinetic energy. So the silver nucleus must have a certain initial speed, or else it cannot move over. Too bad, sorry boss. Alright, so if you want an analogy, it's a bit like something like this lah. Let's say here your height is 0, and then somewhere here 1.62, and then you got a ball. The ball is going to roll up from 0 potential to 1.62. What is the minimum speed of V such that it can reach here? 1.62. Okay, so this is a increasing potential. Great. So we're going to write that in the equation. Increase in electric potential energy will be the same as the decrease in kinetic energy of the silver nucleus. Okay, so you have to find a place to park it in. So I'll say the increase in electric P is equal to the decrease in kinetic energy of silver. Alright, increase in electric PE would be Q delta V. We know the Q, 47 multiplied by the electronic charge. Decrease in kinetic energy will be half mv squared. minus 0 lor. Means why minus 0? Because they want minimum speed lah. Meaning at P, your speed is 0. So the final kinetic energy is 0. So you got this equation lor. You don't go and smart cancel the potential difference and V square. I have written this in a specific way to prevent this from happening. So this is uppercase V. This one here is uppercase V, lowercase v. All right, so I'm going to rearrange here, okay, and I'll bring this down there so there's more place to write my working. All right, so I've moved it down a bit, and I'm going to substitute values now. But before that, I think I rearrange first now, okay? So from here, I'll get V square is equal to 2 Q delta V over M, where M here is the mass of the silver nucleus. So finally, I will get V square. I can substitute already, 2. The charge is positive 47 times the charge of an electron, which is 1.6 times 10 to the power of negative 19, the electronic charge. Change in potential was 1.62 minus 0, because we went from 0 at infinity to 1.62 at point P. All right, divided by the mass. Means I don't have the mass of silver. You got. See this 107? The 107 here tells you that the mass is 107 nucleons, which is 107 multiplied by U. You can find the value of U and E in your table of constants. All right, so please refer to that. 107 multiplied by 1U is 1.66 times 10 to the power negative 27. All right, so you can now press your calculator and see what value you will get. All right, so what I got was 1, after I square root, 11700 meter per second. Okay, and it's generally good habit to write it in prefix lah. So 1.17 times 10 to the power of 4 meter per second. Ding, ding. All right, so where are the marks? If you say or state that the increase in PE, something like that lah, either this one or this one is 1 mark here. Correct substitution is 1 mark. Final answer is 1 mark. All right. So I think that's all for this question from Winter 16 paper, Variant 41, paper 41. This question, right, they didn't lean so much on explanation besides the standard one. It's a heavy calculation-based question with proof. So please make sure you write your proof more thoroughly so that you don't lose your mark. Like mentioned that for this field strength to be 0, 2 things need to happen. Magnitude have to be the same, direction have to be opposite. So make sure you have explanation for both. Okay, this one is a straightforward substitute polarity question. Okay, and finally, you are asked to bring a particle to point P. If you have a potential, all the energy is unlocked. Okay, but later if you want to watch, I'll probably record a bonus video and discuss what happens if this is a negative charge particle. What change? Okay, so another way that is a bit intuitive to see that work is done on the field, or your KE will decrease, or your particle will slow down, is that this thing is positively charged. Sphere A and sphere B also positive charge. You want to bring the positively charged silver nucleus, between two positively charged sphere. You think they like this idea? Sphere A is I'm positive, sphere B is I'm also positive. You want to bring a third positive charge into our area of proximity? No, meaning this one will suffer a repulsion from sphere A and sphere B, causing its kinetic energy to decrease. So this one kind of makes sense one. All right, so anyway, again, understanding these changes in energy, applying the equation, and finding the answer will be the final part. All right, so there will be another video soon we're talking about Variant 4.2, where it is a similar question, but they are asking it in a very different way. Similar scenario, different questioning. That will be in the next video. So if you find this helpful, please like and subscribe to support our channel. Share this with your friends, and I'll see you in the next one. Bye-bye.